Welcome to The Explainer. Today, we're tackling something that usually gives chemistry students massive headaches, the mole. But we're absolutely not going to just sit here memorizing confusing formulas. No way. Instead, we're going to build a really deep, physical intuition for how the universe actually works at a fundamental level. So whether you're brand new to this or just looking to solidify what you already know, you're in exactly the right place. Let's get into it.
To really wrap our heads around the mole, we first need to understand the exact problem it solves. Like, why do chemists even need this concept in the first place? Well, imagine for a second that you're a chemist. Your entire job is to manipulate matter, right? You're joining invisible atoms together to create completely new substances. But here's your fundamental dilemma. You live in a macroscopic world. You're dealing with visible scoops of powders and beakers of liquids. But the actual chemical reactions, those happen between microscopic building blocks. So how on earth can we possibly count invisible particles to make sure our chemical recipes come out perfectly?
All right, let's look at a highly practical scenario. Say we want to combine hydrogen and fluorine to make hydrogen fluoride. When you look at the strict chemical reality of this, one single atom of hydrogen reacts with exactly one atom of fluorine. It is a perfect 1-to-1 ratio. So, to make this reaction happen flawlessly in a lab, meaning absolutely zero leftover hydrogen and zero leftover fluorine, we need to bring together the exact same number of atoms for both of those elements.
But how do we actually guarantee equal numbers? I mean, you could try to count them out particle by particle, a trillion atoms of hydrogen here, a trillion atoms of fluorine there. But obviously, atoms are infinitesimally small. Counting them is literally physically impossible. So you might be thinking, hey, I'll just do what chemists always do. I'll grab a scale. You weigh out exactly 1 gram of hydrogen and exactly 1 gram of fluorine. That should give you equal amounts, right? Well, unfortunately, no. That logic is deeply flawed, and the reason why is pretty simple. Atoms of different elements have completely different weights.
When we look at the relative weights of different elements, we start to see the hidden differences between these microscopic building blocks. You see, most of an atom's mass is packed right into its nucleus. Hydrogen, it's super light. It has just 1 proton. But fluorine is much heavier. It's packing 9 protons and 10 neutrons. In fact, if we compare them directly, a single atom of fluorine is exactly 19 times heavier than a single atom of hydrogen. Because fluorine is so much heavier, 1 gram of fluorine is going to contain way fewer atoms than 1 gram of hydrogen.
And right here is where the absolute genius of early chemists comes into play. Think about it. If a single fluorine atom is 19 times heavier than a hydrogen atom, that ratio holds true no matter how many atoms you have, as long as you have an equal number of both. So, if we take 1 gram of hydrogen, we just multiply it by that magic ratio. We're going to need exactly 19 grams of fluorine. By simply maintaining this 1-to-19 ratio on our lab scales, we guarantee the exact same number of invisible atoms in each pile. And we did it all without ever having to count a single one. So, we've established that comparing the relative masses of atoms is the secret to weighing them out in equal amounts. But wait a second, we're missing a pretty huge piece of the puzzle here. To compare weights, you need a standard unit of measurement, right? If atoms are way too small to just plop on a normal scale, how did scientists ever establish a standardized baseline unit for something they literally couldn't even see?
To solve this massive headache, scientists needed an anchor point, a universally agreed upon standard, and they eventually landed on carbon-12. Let's use a visual metaphor to really picture this. Imagine a single atom of carbon-12 as a perfect microscopic pizza. Now carefully slice that pizza into 12 strictly equal pieces. Because carbon-12 has exactly 6 protons and 6 neutrons in its nucleus, making 12 heavy particles in total, one of those slices essentially represents the weight of a single fundamental particle. And just like that, one perfectly equal slice becomes our universal baseline weight.
The really crucial point here is that scientists took that single microscopic pizza slice and gave it an official name, the Atomic Mass Unit, or AMU for short. By formal definition, 1 AMU is exactly 1/12 the mass of a carbon-12 atom. So, instead of dealing with impossibly tiny, mind-numbing fractions of a gram, chemists now had this super convenient unit custom-built specifically for the microscopic world.
Our pizza analogy perfectly illustrates how we use these slices as a baseline reference for the entire periodic table. When you look at the table and see that helium has a mass of 4 AMU, you now know exactly what that actually means physically. It means a single atom of helium is exactly 4 times heavier than our baseline slice. It weighs 4 slices. Oxygen is 16 AMU, so it weighs exactly 16 slices. Suddenly, the entire microscopic world is mapped out using these tiny relative units.
But of course, right here is where we hit a massive wall.
AMUs are fantastic for comparing single atoms in our imagination or on paper, but you can't just walk into a lab and weigh out 16 AMU of oxygen on a physical scale. Our lab scales measure in everyday units, like grams and kilograms. So how on earth do we build a mathematical bridge from the invisible atomic world of the AMU all the way up to the tangible, macroscopic world of grams?
The solution to this problem is honestly one of the most elegant shortcuts in all of science. Imagine the early chemists scratching their heads trying to figure out how much of a chemical to use. They already knew the relative atomic masses. They knew aluminum, for instance, was 27 AMU. So instead of doing incredibly complex math every single time, they simply agreed on a brilliant rule of thumb. You know the atomic mass? Well, let's just weigh out exactly that number, but in grams. So if aluminum is 27 AMU on the microscale, I'll just scoop out exactly 27 grams on the macro scale. But that raises up a huge question. How many actual atoms are inside that scoop?
To even talk about a number of atoms that massive, chemists realized they needed a completely new word. Think about our daily world for a second. If you go to a bakery, you don't usually ask for 12 eggs. You ask for a dozen. The word dozen just means 12 of something. A score means 20. A gross means 144. Well, chemists created a word exactly like this, and that word is the mole. A mole is simply a grouping word that represents a specific, very large quantity of things. Just like a dozen is 12, a mole is, well, what actually is the number?
The number is 6.022 times 10 to the 23rd power. Let that sink in. Also known as Avogadro's number, that is 602 sextillion things. It is a mind-boggling, unfathomably huge number. If you have 602 sextillion atoms, you have exactly 1 mole of atoms. At its core, it really is just a grouping word, but the sheer, staggering scale of it is exactly what bridges the gap between the tiny atomic world and our human world.
Okay, let's put all of this together and actually build our mathematical bridge. Remember our elegant shortcut? One single atom of aluminum weighs 27 AMU. Now, if you gather exactly 6.022 times 10 to the 23rd aluminum atoms, meaning 1 full mole of them, they will weigh exactly 27 grams on your physical scale. Avogadro's number is the exact translation key. It's the precise number of atoms required to turn a substance's atomic mass unit directly into its equivalent weight in grams.
All right, now that you have this deep physical intuition for how this works, we can finally introduce the formal chemistry term you're going to see in all the textbooks, molar mass. Molar mass is simply the mass of one entire mole of a substance expressed in grams. It's the exact same number as the atomic mass you see on the periodic table. You literally just swap out that tiny AMU unit for grams. That's it.
Let's look at a really practical example with a molecule we all know, water, or H2O. To find its molar mass, we just add up the atomic masses of its individual ingredients. It has 2 hydrogen atoms, which are 1 AMU each, so that's 2. It has 1 oxygen atom, which is 16 AMU. 2 plus 16 equals 18. Therefore, the molar mass of water is exactly 18 grams. That means if you pour exactly 18 grams of water into a glass, you are holding exactly 1 mole, Avogadro's number, of water molecules right there in your hand.
So look at that, we've successfully solved the chemist's dilemma. We know what a mole is, and more importantly, we know exactly why it exists, to allow us to weigh out equivalent numbers of completely invisible particles. But how do we actually apply this when we're solving textbook problems or working in a real lab? Let's take our intuitive understanding and seamlessly map it onto some simple mathematical steps.
Let's say you have 36 grams of water, and you really need to know how many moles that actually represents. Step 1. Your given mass is 36 grams. Step 2, we just calculated water's molar mass, which we know is 18 grams per mole. Step 3, don't just blindly memorize a formula here. Think about it logically. Ask yourself, how many times does the mass of a single mole fit into the total mass I'm currently holding? 36 divided by 18 is 2, so you have exactly 2 moles of water. You're simply grouping the total mass into perfectly mole-sized chunks.
But now, what if you want to know the exact, specific number of individual, invisible water molecules floating around in that glass? Well, it's exactly like scaling from dozens down to individual eggs. If you have 2 dozen eggs, you just multiply 2 by 12 to get 24 eggs, right? Same logic here. Step 1, take your 2 moles. Step 2, multiply by Avogadro's number, because there are 6.022 times 10 to the 23rd particles hiding in every single mole. The result is roughly 12 times 10 to the 23rd molecules. Boom!
You have just successfully counted invisible particles.
First off, chemists needed a microscopic baseline. So they defined this tiny unit of measurement called the atomic mass unit, or AMU, which is essentially just the mass of a single proton. And this made things wonderfully simple at the microscopic level. A single hydrogen atom, which is literally just one proton, weighs exactly 1 AMU. If you look inside a fluorine atom, counting up its protons and neutrons, it has an atomic mass of 19 AMU. It's just this perfect, elegant system for the invisible world.
But here's the catch. Doing physical chemical reactions with one single atom? Yeah, that's completely impossible in a lab setting. So we have to ask, why do chemists actually need the mole? Well, you can't just hand someone 19 AMUs of fluorine. You need tangible amounts: powders, liquids, gases, things you can actually hold in a beaker and weigh on a normal scale. We really needed a bridge to connect that microscopic world of AMUs to the macroscopic world of grams.
And this brilliantly illustrates the solution. Instead of trying to isolate a single invisible atom of carbon at 12 AMU, they decided to just take that exact same number, 12, but weigh it out in visible, tangible grams. They realized that if you weigh out the atomic mass of literally any element in grams, you will always get the exact same number of atoms in your pile. This genius leap right here, that's the birth of the mole concept.
Okay, let's dive into this a bit more and look at what that bridge between the invisible and the visible actually looks like in sheer numbers. Like, what does 1 mole actually mean physically? Well, just like a dozen is an everyday word that always means 12, a mole is simply a word that represents a specific, massive quantity of particles.
And here it is. This massive, absolutely mind-bending number is Avogadro's number, 6.022 times 10 to the 23rd power, and it represents the exact swarm of particles you get when you bridge an element's atomic mass to grams. So if you weigh out 1 gram of hydrogen, you have exactly this many atoms. If you weigh out 12 grams of carbon, you have exactly this many atoms. It's literally the universal translation key between the microscopic and the macroscopic. To make this really tactile, let's try to visualize this scale, because it is a number so huge our brains kind of struggle to even comprehend it. If you had just a single micromole of sand, we're talking a tiny, tiny fraction of a mole, it would equal every single grain of sand on our entire planet. Or, get this, if you had just half a mole of cables, they would completely overflow your entire house. When chemists mix just a few grams of powder, they are literally commanding a swarm of particles vaster than the stars in the sky.
Section 1, the conservation of mass, the predictable behavior of swarms. Let's get into it.
Now that we know how to count these epic swarms of particles by weighing them, let's explore how they actually behave when they collide and react. Because these incredible numbers of invisible spheres don't just act randomly, they follow beautiful, highly predictable mathematical laws. The absolutely crucial point here is that no matter what happens, every single gram of these particles is perfectly conserved and accounted for from start to finish. This is Lavoisier's law of conservation of mass. If you react exactly 2 grams of hydrogen gas with 16 grams of oxygen gas, you don't get 17 grams, you don't get 19 grams, you get exactly 18 grams of water. Nothing is lost, nothing is magically created. It's literally just atomic Lego bricks being rearranged.
Furthermore, whether you melt a glacier in the Himalayas or just turn on your kitchen tap, the mass ratio of those locking particles making up water is eternally fixed at 1 to 8. This is the law of definite proportions. Water is always composed of 1 gram of hydrogen for every 8 grams of oxygen. The source doesn't matter at all. The microscopic geometry of an H2O molecule strictly dictates this perfect, eternally unchangeable macroscopic ratio.
And it gets even cooler if these particles form different combinations. Fixing the mass of carbon at 12 grams means the reacting oxygen behaves beautifully. Notice how the oxygen perfectly doubles from 16 to 32 grams. This is the law of multiple proportions. Just notice how elegant this is. When carbon and oxygen form carbon monoxide, 12 grams of carbon locks with 16 grams of oxygen. But if they form carbon dioxide, that exact same 12 grams of carbon now locks with exactly double the oxygen, 32 grams. It absolutely proves that matter combines in whole, discrete, invisible chunks.
Which brings us to a fascinating new mystery observed by early chemists like Gay-Lussac. Why do gases combine in such simple ratios? They were finding that not just the weights, but the physical space these expanding gases occupied during reactions followed extremely simple whole number math. For example, when reacting, 2 entire volumes of hydrogen gas and 1 volume of oxygen gas predictably locked together to create exactly 2 volumes of water vapor. Notice the utter simplicity of the numbers on this chart, 2 to 1 giving 2. There are no messy decimals here. It's almost as if the geometry of space itself is dictating how these chemicals interact. But, why?
Well, Avogadro stepped in with this revolutionary realization: equal volumes of gas simply mean equal numbers of floating molecules, completely explaining those perfect ratios. At the exact same temperature and pressure, the physical size of the individual gas molecules doesn't actually matter. A 1-liter balloon of hydrogen and a 1-liter balloon of oxygen contain the exact same number of particles. Suddenly, measuring the volume of a gas became a direct way to count invisible molecules.
All right, Section 2, Step-by-Step Problem Solving. Let's slow down the math.
Now that we deeply understand why these rules exist, the math isn't something you just have to blindly memorize. It becomes a logical extension of everything we've just visualized. So let's build our intuition for actually solving mathematical chemistry problems by taking it slowly, step by step. Imagine we have 10 liters of oxygen and 5 liters of methane at the exact same temperature and pressure. That gives us a volume ratio of 2 to 1. We want to find the ratio of the total number of individual atoms in these containers. But hey, don't rush to a formula. Let's just use our intuition first.
We're going to walk through the logic here without rushing. The 2 to 1 volume naturally dictates a 2 to 1 molecule ratio. But then we actually must zoom in and count the specific atoms inside those individual molecules. Since oxygen is O2, each molecule has 2 atoms. Simple enough. Since methane is CH4, each molecule has 1 carbon plus 4 hydrogens, which equals 5 atoms. So we literally just multiply our 2 to 1 molecule ratio by the number of atoms inside them. See? We are just visualizing the particles and counting them step by step.
Okay, so only now do we actually look at the formulas. Now that we have that deep intuition, look at how the mole acts as the ultimate hub, perfectly connecting physical mass, 22.4 liters of volume, and sheer particle counts. If you truly understand that a mole is just a specific, massive swarm of particles, then converting between mass, volume, and particle count is just moving back and forth across that conceptual bridge. It all connects so beautifully.
Hopefully this explainer leaves you marveling at the fact that everything macroscopic we interact with is entirely ruled by a hidden, countable world of microscopic geometry. The water you drink, the air you breathe, it all perfectly obeys the unyielding math of the mole. It really makes you wonder, what other invisible patterns are quietly shaping the reality right in front of our eyes? Keep wondering, keep visualizing, and I'll see you in the next explainer.
Hey everyone, welcome to This Explainer. I gotta tell you, I am absolutely pumped to dive into today's topic. A lot of people hear the word chemistry and instantly picture a giant boring list of formulas you just have to cram for a test. But honestly, it's really not that at all. It is literally the hidden rulebook that dictates our entire physical reality. Everything around you, the air you're breathing right now, the screen you're looking at, the water in your glass, it's all bound by these magnificent, unbreakable patterns.
So, I kind of want you to start by asking yourself a pretty big question. What exactly are these invisible mathematical rules? Like, if we could zoom all the way down, way past what our eyes can see, straight into the microscopic fabric of the universe, what is the actual code nature uses to build the world? Well, today, we're going to totally ignore the mindless memorization. Instead, we're focusing on the deep intuition behind the formulas. We're going to uncover exactly why our universe behaves the way it does.
All right, Section 1, the unbreakable rule of mass.
Let's kick things off with something we interact with literally every single day, mass. This is step 1 in our whole macro to micro journey. Okay, so the law of conservation of mass. Sounds fancy, but it just states that mass is neither created nor destroyed in a chemical reaction. It simply changes form. The total mass of your starting ingredients, your reactants, is always going to perfectly equal your end products. Now, sure, there's a tiny exception for nuclear reactions where a small amount of mass can actually convert into energy. Shout out to Einstein for that one. But in standard, everyday chemistry, the universe keeps a perfectly balanced scale. Things don't just magically appear out of nowhere or vanish into thin air. Let's actually apply this intuition to a quick real-world puzzle. Imagine you've got exactly 4 grams of hydrogen, and you let it react with some total mystery amount of oxygen. Boom! A reaction happens, and you're left with exactly 36 grams of water. Well, because we know the universe's scale has to stay perfectly balanced, we don't even need a complicated formula to figure out how much oxygen we used. We just logic it out. The total at the end is 36 grams. Our starting hydrogen was 4 grams. So, 36 minus 4? That gives us a super neat 32 grams of oxygen. The mass was just conserved and rearranged. Simple as that.
Moving right along to Section 2, Nature's Fixed Chemical Recipes.
Okay, so the universe keeps its scales balanced. Got it. But nature doesn't just randomly mash stuff together with whatever amounts happen to be lying around. It's actually an incredibly precise chef. And that brings us to the law of definite proportions. Basically, this law tells us that a chemical compound is always going to contain the exact same proportion of elements by mass. It totally doesn't matter if you scoop up a glass of water from a raging river in a forest, buy it in an expensive plastic bottle, or build it from scratch in some high-tech lab. If it is water, its underlying recipe of hydrogen and oxygen by mass is always absolutely fixed.
And let me show you what happens when you try to mess with that fixed recipe. Check out water on the left side of the screen. For every 2 grams of hydrogen, you have exactly 16 grams of oxygen. Now, what if we force literally just one more part of oxygen into that mix? We get the compound on the right, hydrogen peroxide. We've still got 2 grams of hydrogen, but now we're sitting at 32 grams of oxygen. Just by tweaking that fixed proportion, we completely transform the life-giving liquid we drink into a super harsh chemical you use to disinfect cuts. Yeah, absolutely do not drink that. And that right there is exactly why nature's fixed recipes matter so much. But hey, what happens when elements do combine in different ways, kind of like what we just saw? Well, that introduces something called the law of multiple proportions. I know, it sounds a little dense, but just think of elements like Lego bricks. You can't snap half a Lego brick onto another one, right? Atoms work the exact same way. They have to combine in whole pieces. Because of this, when 2 elements form different compounds, if you keep the mass of one element fixed, the mass of the other is always going to be a simple whole number ratio. Let's make this concrete. Take a look at carbon monoxide and carbon dioxide. Notice how in both of these compounds, we are keeping the mass of carbon totally fixed at 12 grams. In carbon monoxide, that 12 grams reacts with exactly 16 grams of oxygen. But down in carbon dioxide, it reacts with 32 grams of oxygen. Just compare the oxygen numbers, 16 to 32. That simplifies beautifully down to a 1:2 ratio. No messy decimals, no weird fractions, just perfect, intuitive whole Lego bricks snapping together.
All right, Section 3, the mystery of gas volumes.
Up until now, we've been super grounded in the solid, tangible world of mass, things we can easily weigh. But back in the early 1800s, chemists started studying the floating, invisible world of gases. And guys, they noticed a really weird pattern. A French chemist named Gay-Lussac observed that when gases react, they don't just conserve mass, they also react in incredibly simple, whole number ratios by volume. For instance, if you take exactly 2 volumes of hydrogen gas and mix it with exactly 1 volume of oxygen gas, you don't end up with 3 volumes of water vapor. Nope, you beautifully get perfectly 2 volumes of water vapor. The ratio is just incredibly simple, 2 to 1 to 2. But you know what the absolute agonizing part was for early scientists? Literally, nobody could figure out why this was happening.
So for years, scientists were just completely stuck. I mean, they could measure the volumes, they could clearly see the pattern, but they completely lacked the microscopic intuition to actually understand it. It wasn't until 1811 that an Italian physicist named Amedeo Avogadro stepped up with a massive plot twist that completely flipped our understanding of reality on its head. Which leads us to Section 4, Avogadro's hidden particle world. Avogadro essentially grabbed us by the hand and invited us to zoom all the way down into the quantum realm, the hidden particle world. He built the ultimate bridge between the volume we can see with our eyes and the actual particles existing at the microscopic level. He came up with this beautifully simple hypothesis. Equal volumes of gases at the same temperature and pressure contain equal numbers of molecules. I really want you to let that sink in for a second. It might sound like a basic textbook definition, but it's incredibly profound. It means that the physical space a gas takes up isn't determined by how heavy or wide the individual particles are. Not at all. The volume is a direct reflection of the physical sheer number of particles present. To really build our intuition here, I want you to imagine 2 identical balloons. Now, the first one is filled with helium. Helium atoms are these tiny, single, super lightweight specks. The second balloon is filled with methane. Methane is a polyatomic gas, meaning it's bulky, it's got 5 atoms stuck together, and it's way heavier. If you were to walk down the street and ask a random person which balloon holds more particles, what do you think they'd say? Intuition probably screams the helium balloon, right? Because tiny things pack tighter. Or maybe the methane, because it feels so much heavier. Well, here is the absolute mind-blowing takeaway. Avogadro tells us our everyday intuition is completely wrong. If those 2 balloons are the exact same size, and they're sitting at the exact same temperature and pressure, they hold the exact same number of molecules, period.
The physical bulkiness, the weight of the individual gas molecules, none of that matters. Volume is directly proportional to the sheer quantity of molecules. And suddenly, this finally explained Gay-Lussac's mysterious gas ratios. 2 volumes of hydrogen combining with 1 volume of oxygen meant precisely 2 molecules of hydrogen reacting with 1 molecule of oxygen.
Section 5, the magic molar volume. Okay, now that we deeply understand this invisible link between the physical space a gas takes up and the number of particles inside it, we can bring in a mathematical bridge, a really cool tool that chemists use every single day. But first, to make the math work, we have to set up a controlled environment. Remember, gas volumes expand and shrink if it gets hot or cooled, or if you squeeze them under pressure. So scientists agreed on a global baseline, called Standard Temperature and Pressure, or STP for short. That's set right at 0 degrees Celsius and exactly 1 atmosphere of pressure, which is roughly the pressure right at sea level. This just makes sure that a chemist freezing in Antarctica and a chemist in a sunny lab in California are comparing apples to apples.
And when you put any ideal gas into that highly specific STP environment, this incredible magic number emerges, 22.4. This is the exact volume in liters that 1 single mole of any ideal gas is going to take up. And remember, it totally doesn't matter if it's hydrogen, oxygen, argon, whatever, it's always 22.4.
Let's tie this all together, because it is just beautiful. In chemistry, a mole is really just a fancy word for a very specific, astronomically large number of particles, 6.022 times 10 to the 23rd power. Because of Avogadro's law, we already know that particle count dictates volume. So if you have 1 mole of those particles, they will puff out to fill exactly 22.4 liters at STP. This is exactly how the totally abstract concept of a microscopic particle count translates flawlessly into a physical volume we can actually measure in the real world.
All right, Section 6, step-by-step chemical puzzles.
So look at all the puzzle pieces we have now. We know mass is conserved. We know elements combine in strictly fixed recipes, and we have our magic volume rule for gases. Let's see just how powerful this is by solving a real-world mystery. Imagine you're standing in a lab, and you find a sealed container filled with some totally unknown gas. You measure it. It has a mass of exactly 1.79 grams, and it takes up 2.5 liters of space at STP. And that is literally all you know. No complex sensors, no chemical tests. Can we unmask the identity of this gas using just the intuitive rules we've learned today? Oh, absolutely we can. Let's reason through this step by step.
Step 1. Let's figure out the density. We've got 1.79 grams crammed into 2.5 liters. If we divide those, we find out we have 0.716 grams for every 1 liter. Okay, now for step 2, the magic trick. We know that 1 mole of any gas at STP occupies 22.4 liters. So, if 1 single liter weighs 0.716 grams, how much would our magic 22.4 liters weigh? We just multiply them, 0.716 times 22.4. And step 3 gives us our result, exactly 16 grams per mole. Now, all we have to do is look at our periodic table recipes. What gas has a molar mass of exactly 16? Methane? You've got 1 carbon at 12, plus 4 hydrogens at 1 each. Boom! We just identified a completely invisible gas using pure, step-by-step mathematical intuition.
And honestly, that is the true beauty of this explainer today. Chemistry isn't just a bunch of arbitrary rules made out by folks in lab coats to make tests harder. It's this profound, beautifully interlocking system of mass, volume, and completely unseen particles, all reacting in perfect whole number harmony. So as you go about the rest of your day, look around you. Think about the air, your coffee, the screen you're watching this on. Can you see the precise invisible math holding your reality together? Because I promise you, once you start seeing it, the world is never going to look the same. Thank you so much for joining me on this explainer, and keep exploring.